The last concept I want to talk about here in the context of counting of finite sets is something known as the pigeonhole principle. Pigeonhole principle. The principle is very simple. It says that if you have, let's say that you have n pigeonholes, 1, 2, all the way to n, and you have n plus 1 pigeons. And you want to put these n plus 1 pigeons into these holes. If you put the first pigeon in the first hole here, the second in the second, the n in the nth, where do you put the n plus 1? It has to go into one of these boxes. This is why it says that if you have n plus 1 pigeons and n pigeonholes, then at least one of the pigeonholes has to have at least 2 pigeons in it. Okay, this is really all the principle is saying. Now, without using pigeonholes and pigeons, this is really a statement about functions. That if you look at the function f from a to b, and you say that the cardinality of b is smaller than the cardinality of a, what does that imply? Okay, so you are mapping elements from a to b, but b is smaller than a. Okay, this implies that there are at least 2 elements, a1, a2 in a, such that a1 is not equal to a2, and f of a1 equals of f of a2. In other words, if the codomain is smaller than the domain, then there exist at least 2 elements that are mapped to the same value in b. This is really what the pigeonhole principle is. A here are the pigeons, B is the set of pigeonholes. Okay, so we are saying at least 2 pigeons have to be mapped to the same pigeonhole. And in fact, we can actually extend it, not only that we have at least 2, but if you think about it, that again, if you have f from x to y, and the cardinality of y is smaller than the cardinality of x, then we know that there exists, let's say, a y in y such that the cardinality of the set x, such that f of x equal y, has to be greater than or equal to the cardinality of x divided by the cardinality of y, and we can take the ceiling of this. Okay, so what is this saying here? Again, like, let's look at x. The size of x is 22 and the size of y, let's say 5. Okay, what this is saying is that there is an element y, there's at least one element y, such that the number of elements that are mapped to y is greater than or equal to 22 divided by 5, which is 5 here, right? And just think about it. You have 22 elements in A, 22 here in X, sorry, and you have 5 elements in Y. You know, you have to map at least 5 of those elements. You have to map at least 5 of those elements to the same element in B. Okay, this is what this formulation is saying, and this is sometimes known as the extended pigeonhole principle. So let me show you one example of how. So pigeonhole principle is just a counting argument, and let me show you one interesting example or application of that. It has to do with the graphs. So let G equal VE be a graph with n nodes. I can make the claim that at least 2 nodes in G have the same degree. Okay, just think about it and try graphs with 3 nodes and 4 nodes and 5 nodes. You will not be able to draw any graph in which you cannot find at least 2 nodes with the same degree. Okay, so why is this true? What are the pigeonhole and what are the pigeons and the pigeonholes? So think about the pigeonholes here as the node degrees. Okay, so the pigeonholes are really the set of node degrees. Okay, so it's the set of what are the possible node degrees in a graph with size n. The node can have degree 0 or 1 all the way to n minus 1. And the pigeons is the set of nodes in V, V1, V2, all the way to Vn, okay? And we are saying that we want to map pigeons to pigeonhole. So we map to every node to the node that it corresponds to. So if the degree of node V1 is 5, we map it to pigeonhole number 5, and so on. Now, where does the pigeonhole apply here? So again, if this is x and this is y, if you look at it just at the first glance here, the size of x is n and the size of y is n. So if you look at this, this is not a condition under which the pigeonhole principle applies, because the pigeonhole principle applies only when the size of y is smaller than the size of x. So from a first glance, the pigeonhole principle is not applicable here. But if we think a little bit more carefully, you will not just look at this here, look at this set of possible degrees and pay attention to degrees 0 and n minus 1. And think about the following question. Is it possible that a graph has one node with degree 0 and another node with degree n minus 1? Again, the question is it possible that a graph has at least one node with degree 0 and at least one node with degree n minus 1? The answer is no, because if the graph has a node of degree n minus 1, it means it is connected to every other node. If it is connected to every other node, there cannot be a node with degree 0, because every node has at least one neighbor. If a graph has node of degree 0, then there is one node that's not connected to anything else, and then you cannot have a node whose maximum degree is n minus 1. Using this reasoning, then the set y, the set of pigeonholes, it's really either from 0 to n minus 2 or from 1 to n minus 1. Okay? You cannot have degrees 0 and n minus 1 in the same graph. So now if you look at the size of y, now whether it is this one or this one, the size of y is at most n minus 1. The size of x is n still, it's the same number of nodes, and the size of y smaller than the size of x. Therefore, by the pigeonhole principle, at least there exist at least two nodes in x such that f of x1 equal of f of x2. These x1 and x2 from x are two nodes, and we map them to the same degree. So these two nodes have the same degree. Okay? So this is a nice application of the pigeonhole principle, where you think about the pigeonholes are the possible degrees that a node can take. And now you throw these nodes at the pigeonholes to which they belong. So if a node has degree 7, you throw it at pigeonhole number 7. If a node has degree 0, you throw it at pigeonhole number 0. But keep in mind, again, if you think carefully, that you cannot use pigeonhole number 0 and pigeonhole number n minus 1 in the same graph. Either you have a node of degree 0, in which case you cannot have a node of degree n minus 1, or you have a node of degree n minus 1, in which case you cannot have a node of degree 0. And in either case, we have the size of the codomain smaller than the size of the domain. By the pigeonhole principle, at least two nodes have to map to the same pigeonhole, or in other words, two nodes have to map to the same degree. And this is why every graph with n nodes has at least two nodes that have exactly the same degree.